and every time you take a step, you're braking. So for that study, we tried to capture this braking energy. So like when you hit the ground, you sort of slide a little bit. It's a small slide, and during that slide, you would spin a generator, and then that energy would be captured that you could use to store it or to power something in real time.
Welcome to Boom, where we have biomechanics on our minds.
Boom.
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 Boom,
Boom.
boom, boom, boom.
Boom.
We are here with Professor Pete Shull. Pete is an associate professor of mechanical engineering at Shanghai Jiao Tong University and the principal investigator of the Wearable Systems Laboratory. Thanks for being with us, Pete.
Thanks, Melissa. I really appreciate you inviting me on here. I've listened back through some of the archive of the Boom podcasts, and they're very interesting topics and high quality professional podcasts. So it's very exciting to be on here myself. So looking forward to it.
We appreciate it. I'm sure this is going to be another exciting conversation. And some of my work actually is based on gait modifications that alter the knee adduction moment for people with knee osteoarthritis. It builds off of your work. So it's also cool to connect here on Boom and learn more about the research that you're leading now. But we always like to start off the episode with asking the question of, when did you first know that you wanted to be a biomechanist?
Yeah, when I was young, I always loved playing sports, like a lot of biomechanists do. And so I grew up playing sports, and I grew up in Montana. We did a lot of outdoor backpacking and hiking, and played football and basketball. And then when I went to college, I studied mechanical engineering and really got into robotics in undergrad. And my master's at Stanford, I was studying robotics. And then when I did my PhD, I just realized that all the best robots were trying to imitate humans. Like the human was sort of the ultimate movement machine. And you've probably seen the recent Atlas videos from Boston Dynamics where they have the robot that can do parkour and like jump off a box and do a flip, which is totally amazing. And then a few days later, I was scrolling through YouTube and saw a human jumping on a trampoline, and he did 8 flips in a row. On a trampoline.
You're like, okay,
yeah,
that's
I was
cooler.
just like, oh, that's so amazing. So I think I really got into biomechanics through that route. And then during my PhD, was really interested in not just the assessment, but the training part of it, and how we can actually give people wearable feedback to train their movement, to improve performance, maybe to run faster or prevent injuries, and then to also to treat disease like knee osteoarthritis. And I just thought that's such a cool area because the humans are so complex that we can augment that. And so that's how I got into it.
I wonder what kind of feedback you'd need to be able to do 8 flips on a trampoline.
That is pure feed forward. There's no feedback at that point.
Yeah, you can't have any fear in that equation.
Yeah, that was amazing. I showed my kids that video. He landed face first on a mat.
The painful side of biomechanics.
I'd like to research that topic. Get my grad students to do some testing.
That's what grad students are for, right?
That's right. You
hear it. Pete's recruiting.
If you do this, you might win a $10 gift card. Yeah.
Oh. Well, thanks for sharing. It's always fun to see where people come from. And now, where you are now, you're working on some really interesting projects in your Wearable Systems lab, one of which is hand gesture recognition. And you've even developed an algorithm to detect hand gestures while walking using a wrist-borne IMU. And this seems like a really interesting but challenging task. It's a human task, right? So could you tell us first what motivated you to work on this gesture recognition task and some of the applications of the algorithm that you've built?
Sure. So our lab does all things wearables, Wearable Systems Lab, so sensing and feedback. And I personally have a bent towards research that will get used, usually in industry or somehow more practical. How could this be useful? And so the reason we started that was in 2015. This was an industry project. Samsung wanted us to create some kind of wristband that you could capture gestures with, and they wanted to do EMG and IMU.
Whoa.
And I said, there's no way that's going to work because there's no muscles in the wrist. How can we possibly measure EMG? But they really wanted us to try, so we tried it, and I'm glad we did it. It turns out you can measure EMG in the wrist because the signals will travel up through the tendons from the forearm, and they'll kind of come together, so you get a whole bunch of signals together, and you can actually capture that. And the other thing is, at that time, that's when we started getting into AI and machine learning, because there is a relationship between the EMG signals that you measure here and individual finger movements, but it's so complex that there's no way you can make a model that's accurate enough to be useful. It's just such a complex relationship. So that's when we started using machine learning, and we found that you can use machine learning and capture the patterns on the wrist and map them to finger movements, and it works really well. So that's when we first realized that, wow, this machine learning stuff is going to be very powerful for wearables, and you can actually do hand gesture recognition. So that's how we first got into it. The applications are, I would consider hand gesture recognition a general human computer interface. So another one would be voice recognition. Siri or Alexa, Siri, turn on my TV and flip to channel 4. So it's kind of the next step beyond spoken is you can, instead of doing that, you could just sort of point and like turn on this channel or go to the next one. So it's really to make humans more lazy, is that we don't even want to speak now. It's so lazy. It's like, just go do that. Just go do that. You can sort of do PowerPoint presentations, and we've used it to control drones, which is pretty cool. If you have a drone flying, you can just like point in the direction you want it to go, or up or down, or stop or forward. So it's just a general interface. There's more noble applications, like people who that are deaf and mute and they can't speak. So you can do automatic sign language recognition. So as they're signing things, you can convert that to text or voice automatically, so people can talk to each other. But it's a very general, open area. You may have seen that the Facebook Reality Labs is really leaning into this hand gesture recognition to augment virtual reality and augmented reality, and so trying to capture hand motions. So I'd say it's very practical. A lot of the smartwatch manufacturers really want to get this hand gesture as a new way to interact with different devices and robots. Yeah.
It's pretty amazing. As you were doing that, it was reminding me of the movie Matilda.
I was literally going to say Matilda.
Where she can just like point and like open the blinds, or
Yeah.
But that is so cool. I'm curious, like how sensitive, the EMG is to picking up these signals, or how, depending on where the EMG is located on the wrist, or they're like, we always worry about placing sensors in the wrong spot, or are these algorithms pretty robust to a range of different people and applications and sensor placement?
Yeah, you're clearly studying machine learning because this is the this is the very key question, and the key challenge is, we can train someone to use it, and then you take the wristband off and put it on again. If it's not on in the exact same place, then the training data may or may not be useful, and so you can get varying results. Or I could take it off and then put it on Hannah's wrist, and her wrist size may be slightly different. So that's where it's all about the training data. So if you train a big database, then it can work for all three of us. So it's very similar to voice. We have an Alexa system that we use all the time, and it never used to work for kids, which is nice because our kids were always trying to, Alexa, play, some song that we don't want to hear again, or play Frozen 2 soundtrack, and we didn't want to play that. But unfortunately, they updated their database, like, so now it works with children. And so now children and adults and people can all speak, and it will recognize the same word. And now they have different languages as well. So it's the same thing with the wristband. Is you just need to build up the database. So we need to do training on a lot of people that have similar sized wrists, and the location needs to be in different places. And if you do that, it can work. So we've done other work with wearable systems for estimating like knee adduction moments directly from IMUs, and you have the same issue, which is getting a data set that includes different movements. And as long as the data set captures what people would do and the locations are in that range, then it can work. But the algorithms themselves are fairly robust. It's often capturing the correct data that's clean.
Right.
Yeah. I have a question that is a little bit more to do with collecting this data, and it's coming to mind because we had a debate today between a few labs on motion capture, traditional motion capture systems versus video capture versus wearable systems. And one of the side conversations we were having was with wearables is that it requires such a large database and a large amount of people to train these models. But then how do we get this data? How do we incentivize people to wear the technology to get this data without first being able to like use it or interpret it, if that makes sense? And I'm kind of curious about your thoughts on that, on if you found ways to be able to collect this type of data or get people to use these devices so that you can then train your models to actually have useful information, but not really like starting with that.
Yeah, so how can you incentivize people to use your system when they don't see a direct benefit? Yeah, that is,
yeah.
I think if it's posed in that way, then you're going to lose for sure. They need to see some benefit when they're using it. So,
yeah,
I mean, I could imagine as they're using it, people like to see their own data, right? They like to see reports at the end. So if you're able to give them any kind of analysis when they're done, this is how much you walked, or even if it's more fuzzy and not specific kinematic angles, is you could just give feedback. People are so interested to know more about themselves. Everyone's very self-centered and they want to know about themselves, and you have the whole quantified self movement. So if you can sort of, we're going to let you use this, and this would work on me too, right? I'd want to know how am I walking, or what are the different things during the day. So I think that could be one way. The other comment is you do need a lot of data, but it's way less than you think. So machine learning and AI came out of the kind of visual and searching millions of dog and cat photos online. And in that case, you do need millions of samples because it's such a diverse array. But like when we did our estimating the adduction moment for flat ground walking for healthy subjects, you only need like 15 or 20 subjects to make a universal model, which means you don't need to collect more training data.
Wow.
Because you think about every single time step, you have all these sensors together, and each sensor has so many features. It's actually a huge, like one full gait cycle is a ton of data. That's a ton of information. And it's also very similar to other people, even though from a human to human perspective, there are big differences. But just compared to like if you took any two random people walking on flat ground, there's a ton of similarities. And so you can very quickly pull out features. So I would also say that the data sets required are totally manageable. So this is just an example. It will only work for flat ground and healthy people, but it was only 15 to 20 subjects. So you could redo that with Neo-A patients on flat ground, and that would at least cover flat ground walking for those patient populations. So it's not like we need to wait until we have 1 million people for certain applications. And of course, the more sensors you have, the less trials you need. If you're trying to estimate this with only one wrist sensor and a foot sensor, like the reduced marker sensor set, then that may require more levels of a higher amount of data. But yeah, those are my main comments on that. So yeah, give something people will feel good about and benefit. And then, but yeah, it's also really not as much data as you think you need.
Well, speaking of something that people can feel good about, another project that we notice you're working on is developing energy harvesting shoes, which I could imagine might be incentivizing for some people, especially with one of the reasons I don't like wearing like a Fitbit or Apple Watch or things like that is because I have to charge it. And it feels like everything these days I have to charge. So I could imagine if there was some way I could create my own energy without even thinking about it, that would be awesome. But we'd like to hear you talk a little bit more about what the impact you see here in deriving energy from wearable devices and how that will help advance, the field and where's that going?
Yeah, I think what you said is exactly right. So wearable devices are annoying to charge, and there's other applications where, I mean, if you're going to go on a 7-day, backpacking trip or some of these extreme environments, you just don't want to carry a bunch of battery packs with you. So, and also some wearable devices require more energy, especially feedback or power devices will require more energy than some of the Fitbits are pretty good, right? They can last for a week or even a month, which is pretty nice. So in that case, it might not be as needed. But if you have vibrotactile feedback or some kind of powered feedback, you would want that. And so humans actually, walking is not very efficient compared to a wheel or something rolling down the road. And every time you take a step, you're braking. So for that study, we tried to capture this braking energy. So like when you hit the ground, you sort of slide a little bit. It's a small slide. And during that slide, you would spin a generator, and then that energy would be captured that you could use to store it or to power something in real time. And so that's the principle of it. The key challenge there, which if you talk to Steve Collins or any of these guys, is that it's very hard to not increase metabolic cost once you start changing gait, or if you have gait, to reduce the cost. So I talked to him after we finished our study and realized that they create these new systems, but then they train people like an hour a day for 3 weeks or something. It's super intense to train them on the new gait pattern. And so we didn't do that. We just did a normal like first off study. And so we captured, I think, 1 watt of energy, which is pretty good for walking, but the metabolic cost went way up because people walk differently once you put stuff on there. So I think that's a challenge. Obviously, people are not willing to walk when it's super exhausting or even a little more exhausting. So you sort of need to retrain them to use a new device, just like if you have a new pair of shoes, or I don't have any experience, but people who walk with high heels or something like that, I would assume it's a very different gait pattern. So that was the side comment is gait training is important when you have a energy harvesting device like that.
Yeah, that makes sense. Could you talk a little bit more about that? You started talking about the mechanism behind the shoes and how it's able to harvest energy. And could you also share then how maybe that did affect gait or change how people were walking?
Yeah, so the concept is pretty simple. You have the shoe, and then below the shoe is a plate that's together. And so when you take a step, the top part will slide maybe 2 or 3 inches. And then when you lift up, there's a spring, and it will come back. So every time you take a step, it slides and comes back. It's a fast reaction mechanism. So as it's sliding, there's a generator inside that you're just mechanically spinning it, and then you would capture the electrical energy from spinning that generator. That's the mechanism of how it works. It's a very much a design problem because we're heavy, and when we take a step, there's a ton of force going into this mechanism that you're stepping on top of. It needs to be light, very light, and very strong and robust. So there's a lot of iterations of prototypes getting it to work so that it wouldn't break and it would be light enough and capture the energy. And what we saw is that people actually, what they would do is they would shorten their gaits, their stride length, and so that just naturally they would shorten it so that when they hit the ground, then they would slide, and when their foot came off, the heel, I guess the toe off point would be about the same as if you didn't have this mechanism. So that's kind of interesting. I thought it might be the opposite, where you lengthen their stride, so they end up taking longer steps, but the same amount of energy. I do think it might be possible to do that with training, which would be pretty cool, is you would sort of be walk skating across and taking bigger steps. So it should in theory take like less energy if you were and less energy and you're capturing it. So but it's basically what you want it to be sliding during stance with one leg. So that's what you want. If you're doing that, then you sort of get this free sliding motion and you happen to be capturing that energy in like regenerative braking in a car. But it's hard to train that. So I think what people did instead is they would do most of the sliding right at heel strike, and they would slide, and then it was stable. Once it hit the end of the slider mechanism, then they would lift up their other foot. And so the stride length ended up being the same, but they shortened the first part. Yeah. So it's kind of interesting. Yeah.
Yeah, people never do what you think they're going to. I feel like that's been my experience.
Yeah. The other thing that was weird was, with running, you have heel strikers and forefoot strikers. We had the same thing with this mechanism, but for walking. So half the people would lead with the heel and then slide, and the other half would lead with the toe and then slide, which is very strange because when normal people walk, we don't really see that for normal gait. So, yeah. I don't know. That was unexpected as well. Not sure why.
Yeah. Well, you never know like where those unexpected findings might teach you later on or what those, might be, what people might be doing. So it's kind of fun to get those.
Sounds kind of like moonwalking or something.
Yeah. We were like, we set the limit on how far you could slide. So it's 2 or 3 inches, but what if you made it like a foot or like 2 feet? Then you're really like sliding all the way across the sky. It would be really awesome.
Yeah, you're like almost like roller skating. Yeah.
Yeah. So.
That's awesome. Yeah. Well, these are just 2 really cool projects that you're working on in your lab. Is there any other project that you're working on that you're excited about or want to briefly share?
Let's see. Yeah, I guess one, going back to the first project about hand gesture recognition, is one issue that we found was the size of EMG sensors and IMUs are kind of too big to put inside a wristband. So it really needs to be inside a watch or something to be practical and usable. So we've been trying new sensors, trying to make it smaller and smaller. And our last attempt was to use the barometric pressure sensors inside your phone, but if you cover them with plastic, it actually turns into a highly sensitive force touch pressure sensor, which is pretty cool. So we did that, and then if you move your fingers, if you look at the tendons, there's actually a profile. They'll go up and down, and you can capture that change with the gestures. So that was much smaller, but now the one we're just starting is touch sensors. So it's almost like the touch sensors you have on your cell phone screen, and we're going to cover the wristband with these touch sensors so they can also measure like kind of touch pressure. So that's super cool because they're like less than a millimeter thick, and you can put them inside here, and so that's pretty interesting. And the other thing is we've been experimenting with ultra wideband technology as an alternative to transmitting data, but also you can get position. So as you know, with wearables, we can only ever get angles, right? With IMUs, we can never get position. So the only way we can get position is if we make a model out of the IMU joint angles. And so ultra wideband has seen a resurgence where it's kind of like Bluetooth, but it will give you a position estimate if you have 2 or 3 of those. So we're starting to explore putting those across the body and now measuring positions directly. So it's already been used for stuff like, what's it called? The Peloton, when you're biking with a bunch of people and you want to know where they are, or people running together on a soccer field, you can track their positions relative to each other with beacons. And that's it's within like 10 centimeters. So it's not quite accurate enough to be useful, but we're trying to explore if we could get this down to an accuracy where you could now measure positions on the body, which would be really cool because you could say have one in the wrist and then one
Yeah.
just on your phone or on the chest, and you wouldn't need the whole string of IMUs. You could just get that position directly.
Right.
So that's pretty cool. I remember AJ Seth was asking about this a few years ago. Can you just tell me one sensor that can measure position that's cheap and accurate? And I said,
Yep.
no,
Yeah.
there's nothing out there. It's only joint angles. I'm sorry. So we're hoping
Yep.
that technology could be a potential avenue to get position as well as angles.
That's super exciting. It's so cool to see develop these different wearable systems that seem just so applied across like a range of, from just everyday use to helping people with movement disorders. And it's really awesome to see that. And from some of the systems you develop, you've started companies. With your most recent one is Sage Motion, which is a wearable haptic feedback system. And I guess kind of shifting gears here a little bit, we're super curious about some of the pros and cons of starting a company that stems from your research innovations.
Yeah, well, we started Sage Motion 2 years ago. It was mostly out of like frustrations in the lab. So we wanted haptic feedback, and the only option is to make your own prototype. So prototypes can work well for about one paper, and then you want to pass it to the next student, and the code is so messy, and there's a lot of electrical problems, and the wireless doesn't work, and all this stuff. So and the other frustration was we just needed open algorithms. I know Scott's a big believer in open science and kind of opening things, and most of the wearable systems, they are closed. So all their algorithms are kind of secret, and you don't really know how they're calculating the joint angles. And sometimes they won't give you the raw data. It's processed raw data, and we really need raw data for machine learning algorithms. So, and then the third thing was customization. Sometimes you have to like wear a full body suit just to get a certain angle. And for a lot of these applications, let's say you just want to measure and train the knee flexion angle, you might really only need like 2 or 3 nodes to measure and to give feedback. So that's the reason we started the company, is because of these. There wasn't any commercial systems. I mean, our lab bought most of them, and none of them really worked and were portable, where you could take them out of the lab. So that was kind of the reason that we started it. And we decided to split off the engineering work and the research work. So we wanted a research platform where you could just get in and you could program. And it's in Python too, which is way better for machine learning algorithms. There's so many libraries. So you can get in and just start programming in Python, and you can write your algorithms, and you can use any number of nodes. And so that's the research part, and trying different algorithms, trying different controls. And then the engineering part is, making the wireless signal not break, making it work for long ranges, making sure all the electronics are stable, and making like a quality product is not really research, it's engineering. So there came a point where it became clear to split off those and put all the engineering and support work on one side, and kind of to save time for, sometimes labs want to make prototypes and for learning, which is good, but sometimes they just want to go apply stuff, especially outside of the lab, or they just want to write a new algorithm and they want it to work on the wearable system. So I'd say the pro is that was the vision, and it's worked out really well, because there's a very nice, like, stable platform now as a Sage Motion system that our lab uses for research, but then other labs want this as well. So that's why we decided to commercialize it. So that worked really well. And I think it's nice to separate those out. And then the company is motivated to create a stable system that's really good and beneficial. They don't necessarily need to publish papers, but then the research labs can just spend all of their effort and focus on the algorithms. And then it's open, so they can share it with other labs. It tends to work pretty well for research applications. The cons are, I would say, it just takes a lot of time. Starting a company, going from prototype to product is a huge gap. There's a lot of work that goes in there. So I remember somebody told me at one point, you should not start a company until after you get tenure, because it's just going to be too busy. Yeah, too much time going into it. And I would agree with that. It's better to wait. It's a lot of time. It's exciting, but it's just a lot of time. So I think that's a con, is it can be a lot of effort that goes into it. It's a totally different skill set. But it's also exciting because other people can use it and you kind of see the benefit of that. So yeah, those are the things that jump out.
Thanks. That's super helpful and like nice to hear that perspective, I think. And it's something, we don't always talk about on Boom. Like I feel like we're a lot in the academic side or the industry side, but it's nice to see the harmony in both. And sort of speaking, that was great, I think, advice. And we're wondering a little bit, you've got a pretty rich experience in having done your bachelor's in mechanical engineering in Texas, and then doing your master's, PhD, and postdoc here at Stanford in California. Now you're a professor in Shanghai. So we're interested in hearing about that experience, that transition. What made you want to stay there, and what advice do you have for people that are also thinking about making that switch and starting a lab somewhere that, whether it be a different country or somewhere that's just wildly different from where they've been used to being?
Well, when I was at Stanford, there was a graduate exchange program where you could go to China for 3 months and study in a lab. And so that's the first time I explored that. And so I think my third or fourth year.
Wow.
Maybe similar to you, somewhere around you guys are. So they had a special program, and I went on that to Tsinghua University in Beijing. And at that time, I just discovered the quality of research at the top tier universities in China is really high. It's comparable to Stanford. It's really good. And the government really supports research, and they put a lot of money into research. And at that time, like, it was getting really hard to get funding in the US. The rates were like around 10% or so. And then in China, they were more like 20 or 30% funding rates. So it was a lot higher, and kind of had a feeling of growth and kind of moving forward. And but also from a personal level, we just love the food here. It's so good. It's just,
what's like your favorite?
There's so many things that are my favorite. There's one local dish called Hong Xiao Rou. It's kind of like pork belly, like braised in a sweet glazed sauce. It's just these huge pieces of meat. You can get a dish, a bowl of noodles, but it turns out it's one super long, stretchy noodle that's just delicious. Yeah.
What?
It's got like
that sounds like something I would like.
I think the best food in the world has got to be in France and then China. They just have so many areas of the food. So that was a big draw for me. I love trying new foods. And of course, they've got tons of crazy stuff here that I've eaten cicadas, and I've eaten vegetables that have no English name.
Whoa.
And I've eaten animals I didn't know existed. So it's really been fun. But my wife came with me when we visited, and we also like the culture. It's kind of a group culture. So you join like a family, and even when you eat, it's always around a round table, and you get to share the food. So if you've ever had that experience where you ate with somebody and they got the better dish than you, and you just felt kind of jealous. You felt jealous. Now you can just spin the table, and then you can try the good dish.
That's usually I just have to order what the person I'm eating with orders, or else I just stare at their food the whole night. I have to be careful. They're like, "Hey, I'm up here."
Yeah, next time if that happens and they get something better, just reach over and grab a little and just say, "Oh,
just like,
I thought this was like Chinese food to share," and so I just thought I could have some.
I like that advice.
Yeah. So that was a big draw in coming here, and it's just kind of. It's an exciting place to be. I mean, it's somewhat similar to the Bay Area, just like a lot of new stuff happening, but they run the university like a startup. Every year they have major changes in the university, just major improvements. They didn't have like a formal tenure process when I came, and they put that in place, and they just major changes all the time, which is, you got to get used to that, but it makes it exciting. Some people say the foreigners that come to Shanghai, they stay because it's kind of like a drug. There's so many new things and exciting things. There wasn't really a culture of starting companies when I came 8 years ago, and now they've got a massive incubator that surrounds the campus with like 500 startup companies, like little ones all around. So it's just these crazy changes. Yeah, it's been fun. And then why do I stay? I think probably for similar reasons. My kids are growing up here. They're going to the local schools. My son is in 5th grade. My daughter's in 2nd grade, and my other daughter's in preschool. And the stereotypes are true. They teach math so well here, and his math is amazing. They just do a great job teaching, and we like the schools, and we made friends with Chinese people, and so yeah, we feel pretty rooted here, and so we really like China a lot. The news portrays a lot of the extreme things, which might be true, but it's not a picture of reality. So it's a little sad to see the distortion a little bit. So yeah, it's really a great place to live, and I hope you guys can come visit Shanghai sometime. Would love to show you around, and we can eat some weird stuff or some normal stuff, and just check out the lab.
Yeah,
that sounds great. We want a long noodle.
We like weird things and normal things, so that sounds good.
Okay.
I'm curious too about the culture of just like day-to-day like life and communication, like working in the lab. Like, was there anything like sort of surprising about that, or similar to working, what it's like working with other people in the US? What is on that level? What is that like?
I think it was surprising to me how similar it was. I somehow had this idea that I would need to sort of clock in and be at certain places at certain times. And in the first few years, I was just like, nobody is checking on me, and it's up to me to, do my research and write my papers and grants and teach and stuff. And so that from that side, it was very similar. What's different? I mean, the language is different. I speak Chinese to my colleagues. I'm the only non-Chinese in my group, so that's very different. I just get Chinese emails all the time. I would say there's more of a group culture and more of a help each other, which is kind of cool. So like I'm in a group with 3 or 4 professors, and we have like 3 or 4 labs that we all share. So when I came in, I wanted a Vicon system with Vertex treadmills, Vertex flip belt treadmill, and so that's what was part of my startup package. And then there's another group doing drones research, and they had 8 Vicon cameras as well. So they just decided to combine it to one huge lab with like 16, and then so now we alternate. There's nets out, so we're either running on the treadmill or there's like drones flying around with the net, so they're not like killing people.
But never at the same time.
Not that I know of, maybe when they're gone.
No double booking in that lab.
Yeah. So and like the professors will often go out to lunch together, which I don't know if that happens as much in the US. It's like if people are around, they'll just walk to the cafeteria and eat lunch. So it's kind of a group culture.
So we almost skipped over our question of asking you if you've ever experienced, and not, I guess everyone's experienced a research fail, but if you'd be comfortable and willing to share a fail with us, and what you were able to learn from that experience.
Yeah, sure. So I think research in general is almost always failing. So most of our proposals fail. More fail than succeed, and papers more fail than succeed. So I think everyone knows that you gotta just keep working on those. But we were kind of talking about language, so I just wanted to share a language fail. So since I've been here, I've been trying to speak in the local language, and I've had a lot of times where I said the wrong thing in a research context. So it wasn't necessarily about research, but I can just share I have got many of these stories, but I can share one.
Please, yeah.
And
I already have language issues just in English, so I can't imagine.
Okay. Yeah. And you can decide whether or not you want to keep this in. So when I was a new faculty member here, I think within the first year or two, they had a retreat for all the newish faculty members, and we went to a place a couple hours away and stayed overnight. And on the first night after dinner, we all met together in a big room, and there were about 40 new faculty members, and then all the leaders in the department. So the dean and the vice dean and several others were all there. And we were sitting in a big rectangle, and we were going around with a microphone, and each person was just introducing themselves, where they're from, what their research is, and just saying a sentence or two about themselves. But it was all in Chinese, so I was very nervous. And there's so many people there, and I'm a new faculty member, and all the big bosses are there, and the dean and everything. So as it was going around, it was coming to me, and I was thinking in my head what I was going to say and sort of practicing it. And so when I finally got the microphone, what I thought I said was, "Hi, my name is Peter Shull. I'm from the US, and I study wearable systems for sensing and feedback. And I really love China. I especially love Chinese food and Chinese culture. And just today I tried a new kind of Chinese drink." So that's what I said in my head and what I thought I said. And what I actually said was, "Hi, my name is Peter Shull. I'm from the US. I study wearable sensing and feedback. And I really love Chinese language and culture. And just today I tried Chinese prostitution."
Just today, right before
Just
this
today.
introduction.
Yeah. So that's what I said. And the whole room just exploded with laughter. And I had no idea why. I thought, I thought, they must think my Chinese is so good. They're just laughing with amazement. And they just kept laughing.
Laughing because it's unbelievably good. Yeah.
Yeah. And my
so how did
professor,
you find out? Did he tell
this
you right on the
professor
spot?
leaned over and he said, "Pete, you didn't say what you thought you said." And they just kept laughing. And I tried to give and then I was like, "Oh no, I'm embarrassed." And I tried to give the microphone to the next person, and they wouldn't take it because everyone is still laughing for so long. So that was a huge fail. And that was I was 6 or 7 years ago. And I'll meet new people. I met another person from another department, and he's like, "Oh, Peter. Oh, you're the guy that tried Chinese prostitution." Oh man!
What a thing to be remembered for!
Oh my god!
Yeah.
What a way to meet everyone! Just big splash.
Yeah. It was that was a huge fail that keeps going on and on. So anyway, yeah.
Wow.
Thanks for letting me share.
Fail
We
that just keeps
appreciate
on
that.
giving.
Yeah, exactly. We appreciate that one. I feel like that's one I'm gonna keep in my back pocket to make me laugh.
Yeah.
As you're talking a little bit about the language, the different languages, it was making me think of a conversation I had a while ago about how there's so many amazing research studies around the world, but we only know about a certain percentage of them because we can only read the languages that we can. And I'm wondering if you've as you're able to speak multiple languages, do you feel like you've been exposed to more research than you otherwise would have, or do you feel like there is that barrier there? Are there ways that we can sort of start to overcome those in research?
Yeah, I think the language isn't actually a huge barrier because almost all the research gets published in English here. So one difference is the PhD thesis my students do it in English, but most of the students will publish their thesis in Chinese. So that would be, and theses tend to get read more here. I don't know if anyone's ever read my thesis in the US. They read the papers, but I think it might be because of the language. So they'll write the similar content, but it'll be in Chinese. So people will read other theses here. But I would say language is probably not a big deal, but the regional differences, they'll have some regional conferences, right? That you'll get a lot of people from China and Asia, right? I'll meet people from Australia or Japan or Korea, that it's closer. So that, I think traveling to different conferences is still very important. The World Conference on Biomechanics is in Taipei next year, I saw. So that's in Asia. So I hope that COVID allows everyone to travel there. You're going to get a lot more Asian people there. And you guys can tack on a Shanghai stopover if you end up going to that.
Yeah,
we will.
We will schedule that.
It's already
right
booked.
Yeah. So I actually don't think that language is a big deal, at least in Chinese. Maybe Russian or some other languages have this, but in China, they publish everything in English. So yeah, you can access those papers.
Yeah. Well, thanks for sharing all of that with us. It's so awesome to have your perspective. It's definitely one that that's new to the podcast, and it's really cool to learn about that. Before we ask our last question, how can people learn more about you and your work and your lab?
Yeah, sure. So my lab is wearablesystems.org, and then the company is sagemotion.com. So you can check both of those out to learn more.
All right. Sounds good.
Awesome. Well, we're up to our last question, Pete. This has been so lovely, and we're excited to look to the future with you and ask you what you're most excited about for the future of wearable technology and biomechanics.
So at the ISB conference, there was a debate on sort of machine learning versus musculoskeletal modeling. I don't know if you guys saw that. Yeah, it was a debate, which I thought was super interesting because it's kind of where we're at in biomechanics. Is there's a lot of physics-based modeling research that goes on, and then there's a lot of interest in machine learning. And so what I'm excited about is what their conclusion was combining those two together. So using machine learning to tune these kind of musculoskeletal models, or using musculoskeletal modeling as the core of machine learning. I think that's going to be awesome, and it's because both have their strengths and weaknesses, and so there's so many different ways to model things, and there's so many different machine learning approaches that people have up until just recently mostly been looking at them in completely separate regions.
Right.
And I know that because our lab publishes in some of both, and it seems like there's just a divide. So getting those together is going to unlock some really interesting stuff. Doing machine learning in real time is also exciting. So there's models can now run fast enough to run in real time, which is super cool. Like I mentioned that knee adduction moment estimation with the Sage Motion system. We can do that in real time with the portable device, and so you can estimate this stuff with machine learning. I think OpenSim is supported in Python, and I've seen another recent paper from your lab where they can do that kind of like run OpenSim in a portable system in real time. Is awesome. That is so cool. It's going to take all this stuff out of the lab, and it's going to add on the intervention part from the assessment, which we've already had. So those are all very exciting for me.
Awesome. Thank you. Yeah, I think we're excited about those things too. And I think you've put it nicely in talking about the advantages of both and bringing them together. And it's really cool to see how you've done that in so many different spaces in your work and your experiences. And just also really inspiring to hear how passionate you are about actually having like an application and helping people at the end of all of the awesome work you're doing. So thank you so much, Pete, for joining us today and for sharing all that with us.
Thanks for having me on, guys.
Yeah, thank you so much. This has been awesome, and we can't wait to have a big bowl of noodles in Shanghai.
Yeah, we'll be there. Actually, just a bowl of one noodle.
We can't have a big bowl of noodles. Thanks, Pete.
Yeah, thanks.
Biomechanics off our minds.